So in this lecture we will learn about higher critical speed. So let's talk about the arrangement first. So the arrangement will look something like this. So this is the shaft which has some weight between this thing, between to this thing. So here it is given some angular speed omega. So let W is equal to weight of shaft per unit length and omega is equal to angular speed of shaft so force per unit length at taken element. Suppose we are going to take some element here, so at element is equal to W by G dot Y dot omega square. So the element has the length dx, and from this point to this point the distance is x, and from this point to this point here we can say the distance is y. So here the weight will be acting in downward direction, that is W by G dot Y dot omega square. So EI dot d square y divided by dx square is equal to the bending moment at the cross section xx, that is in x direction, and also we are going to take the shear force, that is EI dot d cube y by dx cube is equal to shear force xx. So in order to calculate the load per unit length, so EI d4y divided by dx power 4 is equal to load per unit length. So we can write EI dot d4y dx power 4 is equal to W by G dot Y dot omega square. Now let me erase this thing first. So we can write after further simplification d power 4 y dx power 4 is equal to W upon GEI dot omega square y, and moving forward we are going to write W upon GEI dot omega square equal to n power 4, and we know that d 4y is equal to n 4y. So after further simplification we are going to get d4 minus n power 4 y equal to 0, which is the solution of y equal to function of x. So the solution consists of the complementary function plus the particular integral, which we have seen in the previous lectures of this course. I think this topic must be going over your head because it requires the understanding of the strength of material part, basically bending moment and deflection part. The solution of y is equal to complementary function plus particular integral, and for this case the particular integral is 0. So the complementary function is equal to d power 4 minus n power 4 equal to 0. So we can write d power 4 equal to n power 4. So d equal to plus minus n plus minus, these are the solutions. And the boundary conditions, you should remember the boundary conditions for this case is first is x equal to 0, then y equal to 0. Second case is x equal to 1, then y equal to 0. The third case is x equal to 0, then d square y dx square equal to 0. And the fourth case is x equal to L, then d square y dx square equal to 0. So so we are going to take this boundary condition for this equation that is y equal to a sine nx plus b cos nx plus c sine hyperbolic nx plus d cos hyperbolic function of nx. So let's move forward. So let me erase this thing first, whole thing. So at x equal to 0 and y equal to 0, substituting in that equation, so we are going to get 0 equal to a sine 0 plus b cos 0 plus c sine hyperbolic of 0 plus d cos hyperbolic of 0. So after applying boundary condition, we are going to get b equal to c equal to d equal to 0, and a sine nl is equal to 0. So to check two condition here, if either a equal to 0, which is not possible, or sine nl equal to 0. So in this case, if equal to 0, then we are going to get n equal to 0 pi by L, 2 pi by L, and 3 pi by L, and so on. While if sin n equal to 0, we are going to get nl equal to 0 pi, 2 pi, and so on. So for this case, we are going to get omega is equal to n square under root of GEI upon W. So So at n equal to pi by L, so substitute n pi by L in this equation. So at n equal to pi by L, omega 1 is equal to pi by L square multiplied by under root of GEI divided by W. Here omega 1 is equal to omega n. At n equal to 2 pi by L, we are going to get omega 2 is equal to 2 pi by L square under root of GEI upon W. So we can see that omega 2 is equal to 2 square times of omega 1, that is so if n equal to at n equal to 3 pi by L, we are going to get omega 3 equal to 3 pi by L whole square multiplied by the root of GEI upon W. So we can see that omega 3 is equal to 3 square times omega 1. So we can substitute the we can obtain the equation of our interest, that is x square times omega 1. So this is our equation of our interest. So let me plot for this thing, the graph, how it would look like nodal graphs for these cases. So the graph for this case is so let me plot one by one. So this is the first case, that is so the graph will look, so this is the natural bow shape. This is the natural bow shape mode where omega 1 is equal to omega n, that is first critical speed, that is the first critical speed is equal to the fundamental frequency. And for this second case, it will look something like this. So here this is called mode, and distance in this case will be like L by 2 and L by 2. So the second critical speed, so the second critical speed is equal to omega 2, which is 2 square times omega 1. Now let's plot the third critical speed. The third critical speed, so here the distance will be L by 3, L by 3, L by 3. So this is the third critical speed, that is for third critical speed, omega 3 is equal to 3 square times of omega 1. So this is the whole case for this scenario for calculating the higher critical speeds. So in the next lecture, we will discuss about like Whirling Spear shaft, which marks the end of this course. So for now, thank you.